This is Divyasri from Tribly Department. This is my CA2 assignment of second BTech second semester. And my topic is slip test and my subject name is Induction Synchronous Missions ISM. And my topic is slip test. First of all, what is meant by slip test? The slip test is a method used to determine the direct axis and in the quadratic axis of synchronous reactance of a silent pole synchronous mission by running it at a speed slightly below the synchronous speed. The silent pole synchronous mission is also speed slightly below the synchronous speed and analyzing the resulting armature current and voltage waveforms. So first of all, the series test is a method used to determine the direct axis and XT and XQ. To determine the XT and XQ, we will use the SIP test method. Determination of XT and XQ. The SIP test is a simple no-load test which is used to determine the direct axis and quadratic axis synchronous reactance of a silent pole synchronous mission. In this test, a small voltage at rated frequency is applied to the three-phase starter winding of the synchronous mission. The field is unexcited and left open circuited. The simplest is a simple no-load test. The simple no-load test is known as SIP test, which it is used to determine the XT and XQ of a synchronous mission, silent pole synchronous mission. In this test, a small voltage rated frequency is applied to the three-phase stator winding of the synchronous mission. A small 3 voltage supply is applied to the synchronous mission when the field winding is unexcited and left open circuited. So here, this is the voltage field winding. This is the field winding. This is the ammeter and this is the voltmeter. This is the prime mover in the three-phase induction motor. This one. We will give a small voltage supply by here. The voltage and the ammeter are connected in series, and we will use small voltage supply to the three-phase induction motor where the field winding is unexcited. And last, this is the open. This is the arrangement of slip tester. The rotor, from above diagram, we can determine that the rotor is given by an auxiliary motor at a speed slightly less than or more than the synchronous speed. The direction of a rotation should be same at the rotor magnetic field produced by the starter. A small voltage reading indicated by the voltmeter connected across the open circuit field winding terminal shows that the direction of the rotation of the rotor is proper. When the rotor is running at the speed, it closes the synchronous speed. When the rotor speed and the synchronous speed is very close, then there will be a small slip between the rotating magnetic field and armature producer. When the rotor running speed and synchronous speed are very equal, or very close, near very close, there is a small slip between the magnetic field produced and armature silent poles. So the relative speed between the armature MMF and the silent field poles is equal to the slip speed. The relation between MMF is the difference between the NS and NR. Since the armature MMF moves slowly past the actual field poles, hence there will be an instant when the peak of the armature MMF wave is in line with the axis of the actual silent field poles. Since where the armature MMF moves slowly to the past the actual field poles, hence there will be an instant when the peak of the armature MMF wave is in line and the axis of the actual silent field poles. These are the two diagrams. This is the silent pole synchronous mission. This is the XQ axis. This is the XT axis, and this is the peak armature wave MMF wave. This is the NS in synchronous speed. This is the N. This is the also silent pole. This is the NR rotating rotor speed. XT axis, XQ axis. Here the peak armature MMF waveform will be here. The axis of the field poles is direct axis or XT axis. In this position, the reluctance offered by the small air gap is minimum, and this results in minimum magnetizing current or I minimum indicated by the line ammeter A. In this position, the armature flux linkage with the field winding is maximum and the rate of change of flux linkage is 0. Hence, the voltage induced in the field winding is 0. If the position of the armature flux linkage with the field winding is maximum, the armature flux linkage and the field winding is maximum, the rate of change of flux linkage will be 0. When the armature flux linkage and field winding is maximum, then the flux linkage is 0. Hence, the voltage, when the flux linkage is 0, the voltage induced in the field winding is also 0. Therefore, D axis can be located on the isoleogram graph. So, this is the isoleogram. This is the open field voltage. This is the armature terminal voltage. This is the armature current. This is the XD axis. This is the Q axis. From the figure, we can determine the XD equals to AB by CD. Here, XD equals to VT into at IA maximum, IA minimum into line, root 3 into IA minimum. After 1/4 of slip cycle, the peak armature when is in line with the quadratic axis. The position the reluctance offered by the larger air gap is maximum. Due to high reluctance, a large magnetizing current is required to produce the same air gap flux. This maximum current I max is also measured from the line ammeter A. In this position, the armature flux linkage with the field winding is also 0. As a result, the induced voltage across the field winding is maximum. Therefore, the Q axis also can also be located on the isolate graph. From this, we can determine the quadratic axis synchronous is given by determine the quadratic axis of synchronous xq. We can determine a dash b dash by c dash d dash. Here xq equals to vt at in the xd we wrote the I minimum. In xq we wrote I maximum. This small difference between xd and xq. And thank you.